We're going to continue our discussion of electricity and electrical current, talking about some basic concepts regarding various arrangements of resistances or workloads. And we're going to start out by talking about resistors or workloads in series and in parallel. The arrangement that you see in A, R1 plus R2 with R3 and R4, is called a series circuit. That is, it's called in a series because all of the resistances are consecutive next to each other and there is no alternative path where the current can flow. B is a connection of resistors called a parallel connection. And the single most important difference is the current itself has choices. When it can make choices as far as which direction and which resistance it can go through. And these choices are dictated by the values of R1 through R4. Now, here's an arrangement of three resistances in series. On the left, you see that the voltage or power source is shown and the direction of current is shown. On the right is a situation where you substitute the three resistors with what is known as a equivalent resistance. And the equivalent resistance in a series circuit is equal to the sum of the resistances of the three resistors. So if you were asked to give the answer to a equivalent resistance given the following diagram, you would say it would be equal to R1 plus R2 plus R3. Now, because there is only one path, the value of the current at any point has to be the same because you cannot create or destroy electrons. So the flow has to be the same regardless of where you are in this series circuit. And since the flow has to be the same and the flow is driven by the voltage has to also be the sum of the voltages that are lost across each resistance. At each resistance, R1, R2, and R3, you would lose potential difference to drive the current across that voltage or across that resistance. And so by the time you complete the loop back to the power source, you would have used up all the potential difference. And therefore, the voltage sum at 3 points has to be equal to the sum of those 3 points. It has to be equal to the battery power that's provided. In parallel, things are a little different because the path is not dictated in one direction physically, but it's dictated by the laws of physics, obviously, and the ability to find the equivalent resistance is a little different. So the equivalent resistance in a parallel circuit, 1 over that equivalent resistance is equal to the sum of 1 over R1 plus 1 over R2 plus 1 over R3. So the equivalent resistance would be equal to the reciprocal of that once the sum is found. Now, because physical laws control all this, the voltage, the current will vary so that the voltage remains the same throughout. And the current becomes the sum of the currents at each point or at each resistance. Now these two slides, these formulas are extremely important to memorize and have in your hand at all times because you will use these. If you have anything to do with electricity, you'll be using these over and over and over again, along with Ohm's law, V equals IR. Now sometimes we have circuits, probably commonly in the real world, we have circuits that have combinations of resistors both in series and in parallel. So let's start looking at the diagram on the left. On the upper left, you see that you start out with R1 and then R1 branches to R7, and then a parallel combination R2, 3, and 4. Then in series with that parallel combination is another parallel combination R5, 6. Now when you work with this sort of situation, what you try to do is circle or isolate either parallel or series combinations that you can reduce to an equivalent resistance, which is what they're doing here. They wrote a circle around R2, 3, and 4, which I would call R subscript 2, 3, 4. They've called it RP. And then I would draw a circle around 5 and 6 as they've done here, and they've called this RP prime. I would call this R5, 6, subscript 5, 6. So now, in this second diagram on the right, upper right, you see that you have simplified the initial from 7 resistances to 4. And those two that have the circle around them are in series. And so you can turn that into an equivalent series circuit. And I would have called that R2, 3, 4, 5, 6 subscript, because you're essentially changing the original 5 resistances to 1 resistance by just summing those two that you just found. Then R7 and this new R2, 3, 4, 5, 6 are in parallel, and you can use the laws for parallel to change that to 1 circuit or 1 resistance that's R2, 3, 4, 5, 6, 7, which is in series with R1, and ultimately you have a single resistance R equivalent. And so you can always take situations like this and simplify them. Now, later in this chapter, we're going to actually talk about situations where that can't be done. And there are certain rules for finding current and resistance in situations like that. Now, here's a situation where you have a 12-volt power source. You move first through a 1 ohm resistance, R1. Then you move into a parallel combination, 6 ohms and 13 ohms. And the question marks, what is I? What is I2, which means what's the current that's going through resistance subscript 2? And what is the voltage across this parallel combination, VP, which would be equal to the voltage across R1 subtracted from the total, because those two are in series with each other. So let's take this and take a look at how we would go about doing this problem. And first of all, I would reduce this to an equivalent. So I would call this, say, R, and I would call it R2, 3. Okay. Now we know that 1 over R2, 3 is equal to 1 over R2 plus 1 over R3. And that's going to equal 1 over 6 plus 1 over 13, which is going to be 6 plus 13 over the multiplication here, which is 78. And if you do the math here, that means that R2, 3 is equal to 78 over 19, and 78 over 19 is 4.1 ohms. Now what that means is that if you substitute these two resistances for a single resistance, it's going to be 4.1 ohms. Now the total here, the equivalent resistance for this whole circuit, is going to equal this. So R equivalent is going to equal R1 plus R2, 3, because those are in series. And so that's going to be 1 plus 4.1, or 5.1 ohms. Now the reason I did that is if you find this equivalent, you can find this I question mark here, because the total current has to equal the total voltage divided by the equivalent resistance. which is going to be 12 divided by 5.1, which is equal to 2.35 amps. So the total current, I, which was one of our questions here, is equal to 2.35 amps. Now we know that means that there are 2.35 amps going across R1 and that there are 2.35 amps going across this parallel combination. So we can find V1. V1 is going to equal I times R1, which is going to equal 2.35 times 1, or 2.35 volts. So that's the volt drop across this resistance. And then it's asking what is the voltage across this parallel combination, Vp. Well, Vp is going to be V minus V1, which is going to be 12 minus 2.35, which is going to be 9.65 volts. Now what that tells you is that there are 9.65 volts across this resistance and 9.65 volts across this resistance, because when you enter a parallel, the voltage remains the same throughout. So that means that I2 is going to equal Vp divided by R2, which is 9.65, divided by R2, which is 6, and that's going to be 1.61 amps. And that I3 is going to equal Vp divided by R3, which is 9.65 divided by 13, which is 0.74 amps. And this total should equal this. And indeed, if you add it up there, you're going to see. Now here's one more problem. Let's take a look at this problem. In a circuit below, give the equivalent resistance, the current, and the voltage drop across each resistor. Now this one's actually quite easy. It's a simple series circuit. But let's take a look at this real briefly. Get a clean sheet of paper here. Okay, so first of all, we know this is a series circuit, so the equivalent resistance is going to be equal to the sum of the resistances. And so the equivalent resistance here is going to be equal to 10 plus 20 plus 30, which is 60 ohms. So that's the equivalent resistance. Now the current, obeying Ohm's law, is V over the equivalent resistance, or 12 divided by 60, or 0.2 amp. And so there's 0.2 amps here, 0.2 amps here, 0.2 amps here. So the voltage drop at each point is going to be equal to I, because that remains constant, times the different resistors. So this is going to be 0.2 times 10, or 2 volts. V2 is going to be equal to 0.2 times 20, which is 4 volts. And V3 is going to be equal to 0.2 times 30, or 6 volts. And sure enough, if you add these three up, you should get the total, which is 12. Let's take a look at one more problem before we stop on this one. And this one is another simple circuit in the fact that we have now a simple parallel circuit. The question here is what is the equivalent resistance and what is the current at each resistance? We know the voltage at each resistance is the constant at 24 volts. Now since this is a parallel circuit, we know that the 1 over the equivalent is going to equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, which is going to equal 1 over 10 plus 1 over 20 plus 1 over 30 plus 1 over 40. So if we say the denominator is 120, so that's going to be 12 plus 6 plus 4 plus 3, or 2225 over 120. Now that's 1 over RE. So RE is going to be 120 divided by 25, which is equal to 4.8. So the equivalent resistance here is 4.8 ohms. Now what that means is that the total I is going to be equal V over R equivalent, which is going to be equal to 24 divided by 4.8, and 24 divided by 4.8 is 5 amps. Now we didn't really ask for that, but that's IT, the total shown here. But what we did want to know is what is I1, I2, I3, and I4 at each of these resistors. Well, I1 is going to be V over R1, which is going to be 24 divided by 10, or 2.4 amps. I2 is V over R2, which is going to be 24 divided by 20, which is going to be 1.2 amps. R3 is going to be V over R3, or 24 divided by 30, which is going to be 0.8 amps. And then R4 is V over R4, which is 24 divided by 40, which is 0.6 amps. Now if you add these up, there's 4.45, so the total is equal to 5.